What is delta L divided by L? It is nothing but change in length to the original length, which is nothing but the longitudinal strain. The stress is due to temperature and is nothing but T, that is thermal stress. So the expression for thermal stress is nothing but Young's modulus into strain, that is Y into strain. Radiations absorbed by the earth will be re-emitted back, and these emitted radiations are nothing but the infrared radiations. Hello everyone, welcome to session 4 of chapter 11, Thermal Properties of Matter. This is Swati from Department of Physics, Vidhyaashram University College, the Temple of Excellence, Mysuru. In this session, we are going to study about thermal stress and a concept of latent heat of vapor, latent heat of fusion, and many more concepts which are related to the properties of matter that acts for the change in temperature in it. So let us begin with our first topic, that is thermal stress. We all know about the concept called stress from our chapter Mechanical Properties of Solids. What is stress? It is nothing but the restoring force that acts per unit area, or simply we can say that the force per unit area is stress. But now we are talking about thermal stress, which means the stress which is due to the temperature, that is called as thermal stress. We all know about the solids will get expanded during heating, or on heating we can observe the expansion in solids. So this is the reason why the gaps will be left in the railway tracks to avoid accidents, because there may be an expansion of the metal due to a high temperature, and also a small gap will be left between the solids to avoid its bending. So this bending of solids or expansion of solids due to temperature is called as thermal stress. And what is the expression for this thermal stress? So we can write the expression for this thermal stress by using our concepts of the chapter Mechanical Properties of Solids. So for example, let us consider a rod of length L and it expands by delta L, which means L is the initial length of the rod. When the temperature increases, the rod will get expanded, that is change in length is given by delta L. So now the change in temperature is nothing but delta T. So now from coefficient of linear expansion, that is alpha L is equal to, as we all know, change in length per unit length per degree raise in temperature is nothing but the coefficient of linear expansion. So from this we can write change in length delta L equals alpha L into delta T. Now here what we can write this expression as, we can just write this as delta L divided by L, which is equal to alpha L into delta T. What is delta L divided by L? It is nothing but change in length to the original length, which is nothing but the longitudinal strain. So strain here is nothing but delta L by L, which is equal to alpha L into delta T. Now we have a concept of strain. We need to write the expression for stress. So what is the general thing which relates the stress and strain? That is nothing but the modulus of elasticity. So we are talking about length here, since we have delta L and L. So we need to take Young's modulus into consideration. Young's modulus is given by longitudinal stress divided by longitudinal strain. So here the stress is due to temperature and is nothing but T, that is thermal stress. So the expression for thermal stress is nothing but Young's modulus into strain, that is Y into strain. So in the discussion of thermal properties of matter, now we have a concept called latent heat. What is the meaning of latent heat? So far we have discussed about specific heat, heat capacity, molar specific heat concepts, and now we are studying about latent heat, which is denoted by L. It is nothing but the amount of heat required to change the state of a substance at constant temperature. Keeping the temperature constant, what is the amount of heat is required to change the state of a substance is called as latent heat. So in that we have a concept called latent heat of fusion, that is nothing but it is denoted by LF. The meaning of latent heat of fusion is the amount of heat required to change a solid state, that is the unit mass of solid to liquid. What is the amount of heat that is required without changing temperature? So if no temperature is changed, or by keeping the temperature constant, what is the amount of heat that is required to change a unit mass of a solid into liquid. So that amount of heat. So this is called as latent heat of fusion. So it is given by the formula Q divided by M, because latent heat of fusion is nothing but amount of heat required by unit mass of solid to convert into liquid. So M stands for a unit mass of solid to convert into liquid. What is the amount of heat that is required is called as latent heat of fusion. So next we have latent heat of vaporization, and it is given by LV. So it is nothing but the amount of heat required by unit mass of liquid to convert into vapor, or to convert the liquid into gaseous state without changing its temperature. So keeping the temperature constant, amount of heat that is supplied to a substance to change its state from liquid to gaseous state is called as latent heat of vaporization. It is given by the formula LV is equal to Q divided by M, where Q is the heat supplied, M is the unit mass of substance, that is basically liquid, to convert into gas. So in general, latent heat is equal to total heat supplied divided by mass of the substance. So SI unit of latent heat is given by joule per kg, because Q is nothing but the heat, that is energy. The SI unit is joule, and in the denominator we have mass, so SI unit is kg. So it is nothing but joule per kg. And the CGS unit of latent heat is per calorie. So latent heat of any substance depends on nature of substance. Depending upon the nature of a substance, the latent heat values varies, and also it is dependent upon the pressure which is associated with the substance. So our next topic is black body. So we are talking about the conduction, convection, radiation. These are the three modes of heat transfer. In the last session we have discussed in detail about all these things. So in discussing about radiation, we must properly know about what is the meaning of black body. We have a concept of black body which is not a new word to all of us. Black body or black body radiation, black holes, all these terms we might have heard earlier. So black body is nothing but the substance or the object which absorbs all the radiation that incidents on it without re-emitting back anything. So we'll call it as black body. Why it appears black? Because it absorbs all the radiation that incidents on it. So when a perfect black body is heated, it starts emitting the radiation. So when these perfect black bodies gets heated, they start emitting radiations, and these radiations are called as black body radiations. So in actual practice, there is no such perfect absorber, no perfect black bodies existed. So lamp black or platinum black are the nearest approach to a perfect black body, because the reason behind why do we wear dark color clothes in winter, why do we wear light color clothes in summer, is all because of this phenomena, that these colors can absorb maximum heat radiations, and our body becomes hotter if we wear the darker clothes in summer, and hence we avoid all those. So generally black body is nothing but the object that absorbs all the radiation that incidents on it. As I told, this is the reason why we choose light color clothes in summer. So they absorbs all the radiation better than light colored bodies, because the amount of heat a body can absorb by radiation depends on the color of the body. And hence in winter, the clothes, to keep ourselves warm, the clothes what we choose to wear are generally dark colors. But in summer, we used to prefer light color clothes to avoid all these radiations and to make our body to feel much more hotter. These are the few practical applications that we come across in our daily life. And the colors, how do they behave like heat absorbers? So let us now know about few more important concepts, that is emissive power of a surface. We all now came to know about how does the body absorbs and what if the body doesn't emit anything else. So emissive power of a surface, that is given by E lambda. So for a given surface at a particular temperature and for particular wavelength range, the amount of radiant energy emitted per unit area per unit time is a constant. This is called as the emissive power. So emissive power and absorptive power are the two important things that we can understand by the simple statements. What is the amount of heat that is absorbed by an object, and what is the amount of heat that the object can emit back? This is called as emissive power. And for a given surface at particular temperature and for particular wavelength, and the amount of radiant energy per unit area per unit time always remains constant. So this constant is called as emissive power. Similarly, absorptive power of any surface at a given temperature and for a given wavelength is defined as the ratio of amount of heat energy absorbed by a surface in a certain time to a total energy incident on it. What is amount of energy incident on a body and what is amount of energy that a body can absorb at that particular instant of time is called as absorptive power. So in the topic of radiation, we have certain laws, one of which is Wien's displacement law. It states that the wavelength for which the radiant energy from a black body is maximum and it is inversely proportional to its absolute temperature. The wavelength is given by lambda wavelength, maximum wavelength we are telling, so it is lambda m, which is inversely proportional to absolute temperature, or we can also write this expression as lambda m into T by cross multiplying this into T, which is equal to B. What is B? B is nothing but Wien's constant. So its experimentally obtained value is given here, that is 2.898 into 10 power minus 3 meter Kelvin. So this is the Wien's displacement law. So to remember Wien's displacement law, we must keep a wavelength, maximum wavelength, which is equal to constant divided by temperature, absolute temperature. So it's so simple and it is so helpful in solving the numericals as well as in the competitive exams. And going forward, what are the applications of this Wien's displacement law? So it is used for estimating the surface temperature of stars and moon. This law helps us in understanding temperature of stars and moon by knowing the maximum wavelength of the radiation and the absolute temperature. When a piece of iron is heated, first it appears red, then reddish yellow. As the temperature increases, the wavelength of maximum energy emission decreases. This can be explained using Wien's displacement law. So as the temperature increases, because we know that the wavelength is inversely proportional to absolute temperature, the best example to understand this is the example of iron. When it gets heated, basically it will be of red, and after that it will become reddish yellow, which means the wavelength decreases by increasing the temperature, which can be explained by using the Wien's displacement law. So next we have another law in understanding the concept of radiation, that is Stefan's law. So what does this law states? So Stefan's law states that the thermal radiation emitted per second from the surface of perfect black body is directly proportional to its surface area and fourth power of its absolute temperature. So it is given by H is directly proportional to its area and fourth power of its absolute temperature. What is H here? H is nothing but the thermal radiation that is emitted per second from the surface is directly proportional to area and fourth power of its absolute temperature. Here this can be replaced by a constant, that is sigma into a to the power t by 4, where sigma is nothing but Stefan-Boltzmann constant and the value is 5.67 into 10 power minus 8 watt per meter square Kelvin to the power minus 4. And this relation was obtained experimentally by Stefan and was proved theoretically by Boltzmann. Hence, it is also called as Stefan-Boltzmann law. So, our next topic is greenhouse gases. So, what are the greenhouse gases? Certain atmospheric gases, they absorb the long wavelength radiations that are emitted from the surface of Earth and radiate it back. Re-emission will take place and they are called as greenhouse gases. Example for these greenhouse gases are carbon dioxide, water vapor, methane, CFCs and etc. The phenomenon in which greenhouse gases in the atmosphere and the surface of Earth trap the long wave radiations and keep the Earth warm is called as greenhouse effect. So the next important topic is greenhouse effect. What is this greenhouse effect? So this is also the word which is familiar to all of us. greenhouse gases, greenhouse effect, global warming, all these things. So basically, the earth absorbs all the solar radiations incident on it and it re-emits back. Radiations absorbed by the earth will be re-emitted back, and these emitted radiations are nothing but the infrared radiations. So the emitted infrared radiations which causes heating effect. How do they cause this heating effect? By mixing with the carbon dioxide and other gases in the atmosphere, they absorb all these infrared radiations and the results in the earth's atmosphere, and we will call it as global warming. So this entire phenomenon is called as greenhouse effect. So what are the examples of this greenhouse gases? Say for example, it is carbon dioxide, methane and water vapor. All these are the greenhouse gases. They absorb all these IR radiations emitted by the earth's surface, and they causes the increase in temperature of its surroundings, and the effect is called as greenhouse effect. Next topic for today is Newton's law of cooling. So what is this Newton's law of cooling? What is the statement? It states that the rate at which a hot body loses its heat is directly proportional to the temperature difference between the hot body and the surroundings. Basically, calorimeter also works on the principle of conservation of energy, which is nothing but heat lost by the hot body is equal to heat gained by the cold surrounding or the cold surface. So this Newton's law of cooling is also stating the same, that the rate at which means with respect to time, how the hot body is losing its temperature is directly proportional to the difference in temperature between the hot body and the surroundings, and T is given by a formula minus dq by dt is directly proportional to T2 minus T1, where negative sign indicates that the heat is getting lost by the hot body. And in this expression, minus dq by dt is nothing but the rate of loss of heat. Here there is a difference between small t and capital T. Small t refers to time and capital T refers to temperature. And T2 is the temperature of the body, that is hot, and T1 is the temperature of surroundings. Let us now derive an important derivation which is based on Newton's law of cooling, that is log of T2 minus T1 is equal to minus KT plus C. To derive at this equation, we must have the knowledge of Newton's law of cooling, which states that minus dq divided by dt is directly proportional to T2 minus T1. That is the temperature difference, or we can write this as minus dq divided by dt is equal to k into T2 minus T1, where k is nothing but the proportionality constant. I'll call this as equation 1. Now I have dq, that is amount of heat that is getting changed, that is the body is losing with respect to time to the surroundings. So I'll take the concept of specific heat capacity. So from specific heat capacity concept, it is nothing but, so from specific heat capacity we have an expression that is C is equal to dq divided by m into dt, because specific heat capacity says that the amount of heat required to raise the temperature of unit mass of a substance. Or we can write this as dq is equal to, multiplying this to the denominator, we'll get m into C into dt. Or we can write this expression, we have here, look at the equation 1, we have dq divided by dt, which means how the heat is flowing with respect to time. So writing this above equation with respect to time, we get dq divided by dt, which is equal to mc dt divided by dt, and I'll call this equation as equation 2. Now compare equation 1 and 2, both the LHS are dq by dt. So we can now equate RHS, and we get mc dt divided by dt is nothing but k into, look at this expression, we have T2 minus T1 but with a negative sign, because here we have minus dq by dt, and this can be written as dq by dt equals minus k into T2 minus T1. So here let us now bring all the temperature terms to the one side and all the other terms to the other side. So I have dt here temperature term, and here T2 minus T1, it is multiplied with k, and if I transpose it will come to the denominator, that is T2 minus T1, which is equal to minus k this dt gets multiplied here into dt divided by m into c. Here k is nothing but the proportionality constant, m is the mass of a substance, and c is a specific heat capacity of a substance, and these three values are constant. Since all these three are constants, I can replace it with one constant term, that is, I'll take it as capital K into dt. Now let us integrate this expression. So what do we get? Integrating the equation, so integrating the above equation, that is integral of dt divided by t2 minus t1, which is equal to minus integral of k into dt. Now we have a standard formula, that is integral of 1 by x dx is equal to log x. We have integral of 1 by t2 minus t1 into dt. So it is of the same form. So I can write it as log of x is nothing but t2 minus t1. So LHS is done now. Now RHS I have integral of k into dt. Now this is of the form integral of k into dx, which is nothing but kx plus c. This is a standard formula. So we can write it as k, in the place of x I have t, so kt plus c. So this is the solution for our integration here. So in the place of integral of dt divided by t2 minus t1, I have got log of t2 minus t1, which is equal to integral of k into dt is nothing but kt plus c, but we have a negative sign here, so it comes with negative sign, that is log of t2 minus t1 is equal to minus kt plus c is the derivation what we have derived with the help of Newton's law of cooling. So in today's session, we have learned so many interesting concepts under important derivation. In the upcoming session, I'll come up with the numerical part of this chapter. Until then, all of you please keep learning. Thank you.